Hey there, class. Mr. Pusky here. Hope you're having a good day so far. We're continuing with the last section of Unit 1, which is Fundamentals of Algebra 1, Foundational Algebra 1 skills, I suppose. And so 1.7 is Properties of Radicals. Our essential question is how do we use properties of radicals to simplify radicals? So we have a warm-up here, which is what are the square roots of these numbers? A perfect square card might be helpful, or you can use a calculator, whatever you want to do here, so you can figure out what the answers are. All right, so square root of 36. 36 is actually a perfect square, so when you take the square root, you're actually going to get a nice number, which is going to be what? It's going to be 6. All right. Any number that's not perfect is going to be kind of a decimal, and so square root of 18, if you simplify it, that's cool. We're just doing an approximation with this, but it's going to be approximately, you should get 4.24. Okay, and we're going to talk about what this all means in a second here. We're just kind of doing our little warm-up, okay? How about number 3, negative square root of 144? Well, the square root of 144 is going to be 12. And the negative is kind of outside the radical here, so we're going to keep the negative where it is. Now, what's the square root of negative 16? Now, what's that saying? That is saying what number times itself equals negative 16? Well, our options, we know 4 times 4 equals 16. But what's negative 4 times negative 4? Oops. Negative 4 times negative 4 equals positive 16, right? So there's actually no way to get a negative under a radical. So the solution for this one is actually going to be no real solution. Okay, so negatives outside the radical is okay, but inside is a problem for us, okay? All right, what is a radical or a root? Yeah, so if you guys want to kind of review this really quickly, if you want to try to fill in the blanks, give it a try, otherwise we'll go through it in a second here. So a radical or root is kind of like, it's the opposite of like x squared. So if you do x squared, the square root of x squared, it just gives you x, right? So basically it's like the inverse operation of a square, right? And if you had x to the fourth, if you do the fourth root of x to the fourth, that's going to give you x, right? So basically it's like the opposite inverse operation of a exponent, okay? It's also saying what number times itself. If you have like the I guess, square root of 25, it's saying what number times itself equals 25, right? So 5 squared equals 25. So the answer is going to be 5, okay? So if you square root this to both sides, you're going to get 5 on both sides, okay? So very cool. We want to think about it as kind of like an opposite or inverse operation, right? So if we have x minus 2 equals 5, the opposite of subtracting 2 is what? Adding 2. Right, so it's kind of the inverse operation. Same thing here, it's just a little bit more complicated, I guess, okay? So like we talked about down here, we use opposite or inverse operations. We want to solve x minus 3 equals 5. We're going to add 3 to both sides. So adding 3 is the inverse of subtracting 3 because it undoes it. Because what's like, if you do let's see, x minus 3 and plus 3, well, what's minus 3 plus 3 going to be? That's going to equal 0, right? Basically, you just get x. It kind of cancels it out. Okay, that's what inverses do. They kind of undo it or kind of cancel it out, right? Same thing with, like, if we had 2 times x. If you divide by 2, well, 2 over 2 is just going to equal 1, so we get 1x or just x, okay? All right, so likewise, we're going to use radicals or roots to undo exponents. To undo what? Exponents, okay? And so we have different types of roots. We have square root, cube root, fourth root, nth root. It can have like a 17th root. It really depends, but these ones are the more popular ones down here, okay? All right, radicals are also operations, though, okay? So like we talked about, so you can fill in these blanks here. I don't want to spoil it for you, so you can fill in these blanks. So square root of 25 is asking what number times itself 2 times is 25. What number was that going to be? It's going to be 5, right? The cube root of 8 is saying what number times itself 3 times is 8. What is this? This is a little bit trickier. It's actually 2, right? Because 2 to the third equals 2 times 2 times 2, which equals 4 times 2, which equals 8, right? So basically, this is called the index here. It's telling you how many times you multiply that number to get what's in the radical, okay? So same thing with over here, okay? So up here we had the index is that. We have the radical symbol. The radicand's what's under the radical. And the radical's like the whole thing, okay? All right, so perfect squares, cubes, etc., fourths, These are going to be numbers that when you take the roots result in a whole number, in a what? Whole number and not a decimal, okay? There's only like a certain few that actually work. Most numbers are going to be non-perfect numbers, which when you take the square root results in an irrational number, which is any number that cannot be written as a fraction or a ratio, right? So rational, think rational, oops, that equals ratio, right? So basically a ratio is like a fraction. So I could do like 1/2 is a rational number, right? You could actually, 7 is actually a rational number because it's 7/1, okay? So if it can't be written as that, those are going to be irrational numbers. Some examples of irrational numbers are like square root of 2, square root of 10, pi, okay? Usually you can tell if a number is irrational on a calculator if the decimal does not repeat or terminate, which means end, right? So for example, 4/10 equals 0.4. This decimal terminates, it ends right here, right? It just 0.4, it doesn't go on forever, so it's rational. But you can even have a number that's like a decimal that does go on forever, but it doesn't repeat, right? It's kind of like wait, it goes on forever, does not repeat. It is rational. It does repeat, I guess, should be what it says here. So basically like 0.22 be like 0.222, the same number forever, right? Or like 0.415. It's basically the same pattern, right? So it can't go on forever. It just needs to like it needs to be like a kind of a pattern that kind of repeats, okay? Because 2/9 is a rational number. You can write it as a ratio, but the decimal does go on forever, okay? Alrighty. So can we always use radicals? Why don't you guys go ahead and try 1 through 6 here and test your theory. See if we can always use radicals. Give them a try. All right, square root of 17. That's going to be, it's not going to be equal. It's going to be approximately. And so if you do square root of 17 on your calculator, you're going to get 4.12. And that's our approximation. How about number 2? Negative square root of 81. Is the negative in an appropriate spot? It is. So square root of 81 is going to be 9, and negative is outside, which is fine, so we get negative 9. How about number 3? Square root of negative 64. This one's going to be no real solution because we can't have a negative under a radical. How about square root of 9? That's a perfect square, so it's going to equal just 3. What's square root of 0? What number times itself equals 0? It's going to be 0. And the last one we have is square root of 30. That's not equal to, it's actually approximately, to be exact, 5.48. Okay, and the reason why it's approximate is because when you round at any point, it makes it less accurate. It's not actually exact, right? 0.4, that's exact because it stops there. But if you do like, it has like a non-terminating repeating decimal, it's going to be like, you can't, whenever you round it, if it's like 0.1, 2, 3, 4, 5, and you stop at 5, but it goes on forever, if you stop right here, it's actually cutting off all these numbers and making it less accurate, okay? So it's not technically an exact number. All right, we're actually going to talk about that next year. We have exact versus approximate answers. If you round, round at all in your calculations, it makes your final answer less accurate. And sometimes we want exact answers. We want what? Instead of approximations with decimals. So a lot of people, when they like use pi, they use 3.14, or 1/3, they use 0.33. But 1/3 is actually more accurate because it allows you to not chop off any numbers. Actually, it's more accurate. It's like if you plug in 1/3, like in parentheses, like this 1 divided by 3, instead of 0.33, it's actually going to give you a better answer at the end if you use it as a number, okay? So if you have to round at all, I would avoid that until the very end of your problem, okay? We have some examples down here. We have reduced inequivalent fractions. Okay, so we're going to be talking about like exact answers when we're reducing radicals and not. So like with fractions, you can reduce stuff. You can do 0.5, right? But these are all equivalent fractions, 10/20. These are all basically 1/2, right? So we have a similar thing with radicals. If we can reduce this, which we'll talk about next, you'll get the same answer here and here. It's just kind of like, basically we kind of reduce the fraction. Basically we pulled out like a 10 out of both of these, right? We pulled out a 10 and then it made it 1/2, okay? So think about it in that way. All right, simplifying radicals now. So we can use the properties of radicals to simplify them or reduce them with like fractions. The product property, what operation is product? It's multiplication, right? Multiplication. So you can split it into like things that are being multiplied into separate things, or you can kind of combine them, okay? So 40 does equal 8 times 5, right? Well, we can split that. If 40 equals 8 times 5, we can write square root of 8 times square root of 5. That's a totally legitimate thing we can do with radicals. What else multiplies to 40? You could also do Well, we know 20 times 2 equals 40, right? So I could also write this as square root of 20 and square root of 2. Or I could do square root of 4, square root of 10, right? So those are all different ways we can write square root of 40. But there's a way we're going to be doing this. Actually, this one's going to be the most appropriate one because we're looking for perfect squares. And 4 is a perfect square, so that's actually going to be a little bit nicer. But in general, you can, as long as it multiplies to what's under the radical, you can split it or combine it. You could also do like, so if we had square root of 2 times square root of 3, that could equal square root of 6. You can go the opposite direction too. Okay? Quotient property, what operation is that? That is division. So you can take a big radical and split it into 2 smaller radicals, or vice versa, right? So instead of doing square root of 5 over 17, we can do square root of 5 over square root of 17, okay? And maybe put a star by this here. Sometimes it's easier to divide than to split up the radicals. So, so for example, if you had square root of, like, I guess 10 over 5, I would not split this up. I would just, what's 10 divided by 5 going to be? It's just 2. I would just keep it like that. So think about if it makes sense to divide first before you split it up, because it can like save you some time, make your life easier, okay? All right, let's talk about simplifying fractions, what we talked about here, okay? So for simplifying fractions, we pull out the greatest common factor, or GCF, that go into both. So 6 is the GCF that goes into 12 and 18, and then we get 2/3, right? That's kind of how we reduce fractions, so we pull out the greatest common factor. For radicals, we do a similar thing, but we're going to use a product property to split them into perfect, into what? And non-perfect numbers, okay? So we have an example down here. We have 45, right? So 9 times 5 is 45, right? Well, what's nice about that, what's the square root of 9 going to be? We can split it up here. We got square root of 9 times square root of 5. Square root of 9 is going to be 3. So now we have 3 times square root of 5. Square root of 5 doesn't have a nice number that goes into it. It's an irrational number. But if we can pull out all the perfect squares that go into it, that's the way we kind of reduce radicals, just kind of like we would with fractions by pulling out the greatest common factor. Okay? It'll be useful to have your perfect square card here. And so, yeah. So why don't you guys go ahead and try a few on your own. We're going to go through how to do this in a second here. But if you want to give them a try and see if you can refresh your memory, go ahead and try 1, 2, and 3. And then we're going to do number 1 in 2 different ways. I'm going to show you 2 different ways that I think can be helpful. All right. So for number 72, number 1 is square root of 72. The perfect square, the greatest common perfect square that goes into this is 36. So I'm going to write square root of 36 times 2. So the square root of 36 is going to be 6. We get 6 square root of 2. All right. And so let me explain where I got this from, okay? What I like to do, this is called the big to small method, okay? So we'll do that first over here. So it's big to small. Okay, big to small method, okay? So what I like to do is I take the number under the radical, which is 72, and I divide by all the perfect squares that are at or below 72. So I would divide by 64. So 72 divided by 64, what's that equal to? Let's check it. 72. So 72 divided by 64 is like 1.125, right? So that's not the right answer. We want to find a nice whole number that goes into 72 that are perfect squares here, okay? Then I would do 72 divided by 49. And then that's actually going to be our decimal too. But if I did 72 divided by 36, that equals 2, right? So I get, basically what our answer is going to be square root of 36 times square root of 2. Because 36 times 2 is 72, and that's where I got this from. But the nice thing about that is when I take the square root of 36, I get a nice whole number, which is because it's a perfect square, okay? So that's called the big to small method. If you want to try 2 and 3, I'll give this a try. Otherwise, we'll do it a different way in a second here, okay? All right, number 2. So square root of 192, I would divide by, let's see here, for perfect squares, I would divide by 169, then 144, 121, work my way down until I got a number that works. And in this case, it's going to be 64. So I get square root of 64. And 64 times, what is that? 3 equals 192. Well, what's nice about that is what's the square root of 64 going to be? It's going to be 8. So we get 8 square root of 3, and that's our reduced radical. Feel free to try the last one if you want. You want to do one more example? All right, square root of 180. So we start at 180 or below, so that would be what? Let's see, 169 again, 144. Keep dividing down. The, I guess, biggest perfect square that goes into 180 is 36 again. So we get square root of 36. And 36 times 5 is 180, so we get 6 square root of 5. Nice. All right, so that's called the big to small methods, where you kind of start low, start high underneath the what's under the radical and work your way down. The small to big method is going the opposite direction. So instead of doing the big to small method's over here, right? So instead of that, what we can also do is we can do 72. We can work our way this way and go up, right? So 72 divided by 4, what's that equal to? Let's check that. So 72 divided by 4 is 18, right? So I can write this as square root of 72 as square root of 4, and 4 times 18 equals 72. Well, what's the square root of 4 going to be? It's going to be 2. But the problem with this is that now we focus on the 18. Is there any perfect squares that go into 18? Well, 4 doesn't go into 18. Does 9 go into 18? It does. We can break this 18 up now into square root of 9, and 9 times 2 is 18, right? And so for this, square root of 9 is going to be, we have 2 times square root of 9 is 3 times square root of 2. And then the final answer, we can't do anything with square root of 2. No perfect squares go into that. But 2 times 3 is going to be 6 square root of 2. So see, we got the same answer, just took a little bit extra steps. But this way is kind of nice. You have some really big numbers. And it's like, instead of like kind of dividing tediously by all the numbers underneath, like if we had like 1,080, might be nicer to kind of break it into smaller pieces and just keep whittling it down until you get to the final answer like we did here, okay? So yeah, and you can see that 2 times 3 is the GCF, or kind of the 6 times 6 is going to be 36. It's kind of the same thing. So 2 different ways to do that there, okay? All right, let's talk about rationalizing the denominator now. Mathematicians do not like it when we have radicals in the denominator. To fix this, all we need to do is multiply multiply by the number in the denominator, by the what? Denominator. Okay. And yeah, and then also we're going to write here, you just simplify if needed. Okay, simplify if needed. All right, so let's go ahead and do this here. So let's do number 1. So number 1, we have 2 over square root of 3. Is there a radical in the denominator? There is. So what we're going to do is we're going to multiply top and bottom by the square root in the denominator, which is what again? Square root of 3. So we're going to multiply by square root of 3 top and bottom. So what's 2 times square root of 3? Well, on top, that's just going to be 2 square root of 3. You can't combine a whole number and a radical. And what's the square root of 3 times square root of 3 going to be? Well, if we use our kind of product property, that'd be square root of 9, which just equals what? Equals 3. How about square root of 7 times square root of 7? That's going to be square root of 49, which just equals what? It equals 7. See how that kind of cancels it out, makes it nicer? Basically, like, so square root times itself is just going to be the number under the radical. Okay? All right, very cool. Why don't you guys go ahead and try 2 and 3? Number 3 might require a little bit of a different idea, but see if you can give them a try. Okay, number 2. Do we have a radical in the denominator here? We do. We're going to multiply top and bottom by square root of 7. So now on top we have 5 square root of 7. Those don't combine. Over square root of 7 times square root of 7 is going to be 7. So we get 5 square root of 7 over 7. You also want to check if 5 and 7, the numbers outside the radical here, can be reduced. Like if it was like 2 and 4, you would reduce that. But in this case, we can't do that. All right, number 3. We have a radical in the denominator. We do. We're going to multiply top and bottom by square root of 6. So now on the top, we have 2 times square root of 6. Square root of 6 times square root of 6 is just going to be 6. And this is what I was talking about here. You see how we have like 2 and 6? Kind of like this is like a fraction on the left here. So what number goes into 2 and 6 nicely? 2. 2 goes into 2 1 times. 2 goes into 3, or sorry, 6 3 times. So we're going to get 1 or just square root of 6. 1 square root of 6 or just square root of 6 over 3. And that's going to be our answer. Nice. All right, we got some mixed practice here of various things we covered in this lesson. Why don't you guys go ahead and try 1 through 6, and we'll go through them in a second. All right, number 1, we have square root of 80. So this one, I would probably find a perfect square that goes into 80. In this case, it's going to be 16, so square root of 16 times square root of 5. Square root of 16 is going to be 4. We got 4 square root of 5. There's our answer. Number 2. This one's a little tricky. You could multiply the 2 and 16 and make it square root of 32. I kind of like tricked you here a little bit, though. So square root of 16 is just 4. So you can put this in front here. So it's going to be 4 square root of 2. If you did square root of 32, you would just go ahead. You get the same thing again. It'd be square root of, you did square root of 32. Oops. Square root of 32. You would get square root of 16. Square root of 2 again. It's basically just the same thing, just flipped around here. Okay? Number 3. Now, we could split this if we have a fraction of radicals, or a radical of a fraction here. We could also divide it here. What I'd probably do is divide this, right? So 136 divided by 8 is going to be 17. We just get square root of 17. I would just divide what's under the radical here. Very cool. All right, number 4. We have 5 times 48. So the 5 is fine. We need to find the square roots that go into 48. What's the biggest perfect square that goes into 48? I think it's 16. So we have 16 times 3. Square root of 16, square root of 3. Square root of 16 is going to be 4. So 5 times 4, square root of 3. So we get 20, square root of 3. All right. All right, how about number 5? We got 100 times all of these. So for the most part, these top ones are basically perfect squares. So square root of 100 is going to be 10. Square root of 9 is 3. On the bottom, though, we have 18. We can split that up into square root of 9, square root of 2, right? So now we can go from here. Square root of 9 is going to be 3. So now we have 10 times 3 over 3, square root of 2. We can reduce this fraction now. 3 goes into 3 one time, 3 goes into 3 one time. Put this over 1, we can multiply like a fraction, right? So now we have 10 over 1 times 1 over square root of 2. You could also have kept the 3's there and multiplied. That would have been fine. So now what we have is we have kind of long here. We got 10 over square root of 2. Are we done here? Not quite. We have a radical in the denominator. We need to rationalize it. So we're going to multiply top and bottom by what? Square root of 2. So now we have on top 10 square root of 2 over 2. And the last thing we can do is we can reduce that 10 and 2 because it's kind of like a fraction. 2 goes into 2 once, 2 goes into 10 5 times. So we get 5 square root of 2. All right, that was a tough one. All right, very cool. Number 6. What I might do for this one, let me just double check this here. I would also see if, maybe that won't work out, never mind. Okay, I was thinking if you could multiply these all out and get a nice number like 900, but it doesn't do that. So let's go ahead and do it step by step here, okay? What I might do is do 16 because it's a nice number. So square root of 16 is just 4. So we got negative 4 times, and then 3 times 15 is going to be 45, okay? All right, we got to find a perfect square that goes into 45, which is going to be 9. So 9 times 5 is 45. Square root of 9 is going to be 3. So we got negative 4 times 3 times square root of 5. Then negative 4 times 3 is going to be negative 12 square root of 5. Okay. And just so you guys are aware, let me go back to an easier problem here. So if I do square root of 80 on my calculator, right? Square root of 80, I get 8.94 approximately, right? 8.94. And if I do 4 times square root of 5, just to show you what we're doing here, we also get approximately 8.94. So it's basically the same thing like if you had like 1/2 and you had 3/6, right? It's basically they're equivalent fractions. These are equivalent radical expressions. We're just kind of simplifying them and making them easier to work with by pulling out perfect squares, okay? All right, we have some space for extra problems during class if we need them. That's all I have for you today. Thank you for watching. Have a great day, and we'll talk soon.